The other type of uniform motion is the uniform motion with a constant acceleration. In this presentation, we're going to demonstrate a race car is going to move with different velocities, with increasing velocities along the racetrack, while the video camera is recording the displacements in each instant, and the digital camera and the digital clock recording the time. All the data observed in here will be plotted in this graph for the displacement versus time, where the displacement will be measured in meters and the time is in seconds. As the digital clock recorded the first second of the motion, the video camera gives us the first displacement, and it's plotted in here. At the time t equal 2 seconds of the motion, the video camera recorded the displacement with respect to the end of displacement in the first second, and then it's plotted in here as second. At time t equals 3 seconds, another displacement, number 3, is recorded with respect to the previous one and is plotted in the graph as well. At the 4th second of the motion, another displacement, 4, is also recorded and plotted in the graph as shown. We can draw a curve from the starting point, from the origin, that passes through the heads of all displacement, and this curve is parabola-like. The red crosses on the curve represents the end of the displacement with respect to the origin each time, in the first second, and the second, and the third, and the fourth. By projecting lines from each second to intersect with the curve, and then drawing a tangent at this crossing with the curve, these tangents at each instant of time will be obtained, and the slope will tell us the velocity at each instant of time. Different velocities are obtained at different instants of time, and the velocity in here is increasing uniformly with time. By plotting the velocities obtained from the graph of displacement versus time with the time, we're going to get a straight line of velocity versus time, where obviously the velocity is in meter per second. The arrows in beige indicates the uniform increase in velocity v1, v2, v3, and v4 at each instant of time, and it's drawn in the graph of velocity versus time. The velocity from this straight line is actually equals to a slope multiplied by time. And this slope, of course, we're going to get a constant, and this constant has a physical meaning. We define the average acceleration in 3 dimensions as the change in velocity divided by the time interval. Obviously, in 3 dimensions and in Cartesian coordinates, we're going to have 3 components of this acceleration, and as a vector quantity, this acceleration has a magnitude and direction. The simple form of the acceleration as written in one dimension is equal to the final velocity minus the initial velocity divided by the final time minus the initial time. Again, the average acceleration is a vector quantity. It has a magnitude and direction. And the difference between the final velocity and the initial velocity is going to specify whether the acceleration is positive or negative. To define the instantaneous acceleration is nothing more than the derivative of the velocity vector with respect to time in 3 dimensions. And in 1 dimension, it is simply the derivative of the velocity along the axis by which the particle is moving with respect to time. As we started from the graph of the displacement versus time, and we obtain the velocities from here, and then we draw another graph of velocity versus time. When this graph, the relation is obviously linear. From this relation, the slope gives us the instantaneous acceleration equals to the average acceleration. This indicates that this uniform motion is uniform with a constant acceleration. Finding the slope from here, we're going to get, of course, a constant. The constant we talked about in previous slides is the acceleration. And if we plot the acceleration versus time, is going to give us a constant in the third graph.
A ball rolling down a long incline will be used to show how position, velocity, and acceleration of the ball change as it moves down the incline. 5 lights arranged along the length of the track flash simultaneously once per second. As the ball rolls down, it is directly above each of the lights just as they flash. This gives us a record of the positions of the ball at 1 second intervals. This is how far the ball traveled in the first second. This is how far the ball traveled in the first 2 seconds, 3 seconds, 4 seconds. We will move this distance up to a graph to keep track of position versus time. Does position change linearly over time? Next, we will graph the average velocity of the ball during 5 different intervals to see how velocity varies as the ball rolls down the incline. The ball moved this far during the first second. It moved this far during the next second. This far during the third second. The fourth second. This gives us a graph of the velocity of the ball over time. Does velocity increase linearly? Now we will graph the changes in velocity versus time by graphing the differences in successive velocities. What does this tell us about the acceleration of the ball? The acceleration is constant. The glider's velocity increases with time. It accelerates. If we increase the tilt of the track by doubling the height of the shim, the acceleration increases. When the shim height is increased to 3 centimeters, the acceleration increases again. This split-screen view shows the glider accelerating at all 3 angles of tilt.